So now that we have a little bit of a background understanding of light, we can go into how we use light to do analytical measurements. The most common way that this is done is using light absorption. So if we have a molecule starting in some ground, we call this the ground state, right? The lowest energy, it's just hanging out, doing its thing. We have light that comes in, and it can be absorbed by that molecule to go up to some excited state. And this can be multiple different types of processes that cause this, right? This can be promoting an electron from the lowest energy orbital to something higher. It can be starting a molecule, right? Starting a bond vibrating inside of a molecule. It can be the molecule starting to spin, right? These are all different ways that molecules can absorb light, and that energy gets absorbed into the molecule and causes some physical change. In physical chemistry, which is what I mostly study, we look at how we can characterize these specific states. For analytical chemistry, we don't really care about what these specific states are. We just care that the light absorption happens, and we're usually looking for something where we have a very strong signal of this light absorption. And so I will also just mention, we'll get to this later in this chapter, we can also have emission of light, where we have a molecule that starts in its excited state and emits light going down to the ground state, or a lower state, it doesn't have to be the ground state, and emits a photon, and we can observe that light as well. So this would be called emission spectroscopy. Whereas what we're first considering here is what's known as absorption spectroscopy. So in absorption spectroscopy, we're looking for, if we shine light on a sample, we're looking for some of that light disappearing, right, being absorbed into the molecule. Now, the basic way we do this, I can just walk you through the basic outline of a normal spectrometer or a spectrophotometer. Let me spell it right. Spectrometer layout. So what we need some way to produce light. Again, this is for an absorption light experiment, so we need a source of light. In an emission experiment, the light is provided, you sometimes need a light source. It depends exactly what you're doing. That light will get sent out. We will pick a specific color of light using something known as a monochromator. All right, so that selects a specific wavelength, or we can say frequency or color. And then after we've selected a specific color, that will go through our sample. This is often contained in like a cuvette or something like that. I've seen this spelled different ways like that. And then the light will go onto, this is often represented as like an eye here, a detector, some way to measure how much light there is. And we're looking for the change. And so this is often represented as P0, the amount of power that light produces. So this is before the sample, or before the sample, or usually what's done this with a blank instead of our sample in there. And we did this with our experiment earlier this semester. And then we compare that to P after the sample, right, where we have something that is absorbing some of that light. Now, to determine how much light was absorbed, we compare these two values, right, P naught and P. So P naught, this is the amount of incident light. And rather than measuring it actually before the sample, we measure with a blank. This blank will usually just contain either just the solvent or something like that you're using. So often just water if we're doing aqueous samples. And P, sometimes it'll also include the reagents using. P then is our amount of light after passing through the sample. Just reiterating what I said earlier. Now to actually quantify this, we take a ratio between these. So T, we call the transmission, is defined as P over P naught. So this will basically be percentage of light that makes it through. So if T is equal to 1, all of the light went through, nothing was absorbed. If T is equal to 0, all of the light was absorbed, nothing made it through. So this will range from 0 to 1. And again, 0 meaning all light absorbed, 1 meaning no light absorbed. To use this for quantitative measurements, there's a different variable that we monitor because it's proportional to concentration, and that is what we call the absorbance of a sample. And absorbance is related to the transmission. The absorbance is equal to the negative log base 10. You can also do this with natural log, but typically this is done with the base 10 logarithm of the transmission. Or we could say this is the log of P naught over P, just using properties of logarithms. The negative sign disappeared just because we can swap the fraction. Properties of logarithms, if we have a negative sign in front of the logarithm, that's the same thing as taking the top and bottom and swapping our fractions. Okay, so that's what we use to quantify samples, because according to the Beer-Lambert law, the absorbance of a sample is equal to the molar absorptivity epsilon, the path length B times the concentration. And this is an equation you've seen already before in your chemistry career, but just to remind you what all these are, epsilon is molar absorptivity, and this is in units of molar to the -1, usually centimeters to the -1. B is our path length, so this is how long does the light go through our sample, and this is usually given in centimeters. And then C will be the concentration, generally in units of molarity.